Alright, this is Physics 2211, Lab 1, the analysis of a object in constant motion. So, this lab involves the application of Newton's second law, and we're going to be doing that by using it to predict the position of something moving at constant velocity, or basically the sum of the forces being zero acting on an object leading to no acceleration. And in this lab, I went ahead and used a tennis ball and I applied Newton's second law to observe how it rolled on the floor once I tapped it initially to give it a little bit of momentum. And then all of this is going to be uploaded into a software called Tracker. And we're going to do this in order to basically analyze the motion going frame by frame. And then we're going to go ahead and use that to find the initial conditions and put it into GlowScript to then go ahead and model what it should look like and then view the accuracy of it. So some formulas that we need to know are Newton's second law, which is the final velocity is equal to the initial velocity plus the net force acting on an object divided by the mass of the object, all multiplied by the change in time. And since we're working with a constant velocity, that means that there's going to be no net force on it. So V final is going to be equal to V initial. And then lastly, the position update formula is the final position is equal to the initial position plus the average velocity times the time. So once you upload everything into Tracker, you're going to be going key by keyframes, and you're basically just going to be plotting it, as you can see that I was doing on the left side of the screen. And then you can basically go and look at the individual plots, and for mine, I had to go ahead and do a position plot. And so that is the overall shape of the graph that I generated, as well as some of the measurements. Now, the total length of time covered in the motion was about 2.4 seconds, and then the total distance covered during that was 0.496 meters. And then I went ahead and used the velocity capture function by Tracker, and I got 0.28 meters per second. So then, going into GlowScript, I had to input all of my initial conditions. Ball.m is the mass of the tennis ball, which I got to be 0.57 kilograms. And then the initial position would be 0.0 in the x, y, and z direction, because you go ahead and establish your origin. And then the velocity vector is what we previously found. And since it was only moving in the x direction, or the horizontal direction in the positive direction, we know that's going to be a positive 0.28, which was also given by Tracker. Lastly, we have our time, which we're starting at time t is equal to 0, and then we're doing a change in time of 0.01. So then, moving on to GlowScript, we need to actually work on our model. And so what I did was I went ahead and set while t is less than 2.4, since that's the total time of the movement. Then continuing on, then we need to calculate the net force, but we want this to be 0, so we have a constant velocity. Then we're going to go ahead and update our velocity formula by doing ball.vel is equal to ball.vel plus f net divided by ball.m times delta t. And then we're going to do the exact similar thing for position and update the position by ball.pos is equal to ball.pos plus the previous found velocity times the change in time. And then we're going to advance the time by t is equal to t plus delta t. And then we're going to continue doing that. So after I actually finished my GlowScript model, I went ahead and I ran it, and this is what we got. We can see that the yellow ball, which is the initial position, it moved to some amount to the right, which was the blue position, or the blue ball. And then we can see that our position versus time is a straight linear graph, and our velocity was stuck at 0.28 since there's no net force acting on it. However, this is not perfectly accurate. It was accurate for the first, I would say, about 1.25 to 1.5 seconds, as there's little to no deviation from what was observed within Tracker. But then beyond that, it started deviating more and more. And so that just means that overall our model was very good. It just had some slight variations, and that could come down to a couple sources of error, such as not having a perfect motion or not having other things acting on it, such as friction or something related to that. But it's a good approximation. So if we went ahead and flipped our axes, i.e. if positive x were switched to negative x, the only difference would be in the actual kind of motion of the graph. It would start high and then goes more and more negative. And for the linear line, it would just go completely negative. and it would still be a linear plot. And then we cannot determine how many forces, pushing and pull, are on this object. We can know of some that could like contribute to this, such as friction or air resistance, but we cannot know the total amount of forces acting on it, because all we know is that would have to equal to 0. So there could be an infinite number of forces. All right, thank you.